charge density on the iron center, slightly different from what we've seen before. We have charge density now back on the porphyrin rings for our LUMO. More interestingly is that if you recall, with our Surrey transitions, that those were in the LUMOs partially localized on ligands. It's not anymore, it's back on the porphyrin ring. Another interesting thing is that if you plot energy as a function of time during the molecular dynamic simulations, what you notice is that there's this huge gap, or drop, I should say, in potential energy or increase in kinetic energy for the direct collision. Intuitively, you would think this may actually correspond to either a bond forming, breaking, or some reorientation of a molecule in a kinetic barrier. However, at these time points, there are no ionic positions or atomic positions that can be related to forming bonds or breaking bonds. All right, so in conclusion, the hydroxide nucleophile here, when it directly collides with the NO, does proceed with the reaction. This is kind of supported that the reaction actually has happened by the reorganization of the electronics between it did not undergo reaction and when it did. And one could state that the reaction appears to be thermodynamically favorable, but that may be an artifact in how the simulation was ran. And there's plenty of future work one can do with this on a kinetic standpoint or a thermodynamic standpoint. But one would like to relate reductive nitrosylation susceptibility to the iron 3 iron 2 redox of said proteins.
Okay, let's thank Zach for interesting presentation. Presentation is open for discussion. Any questions? I have one. You are telling that you have iron 3, iron 2.
Mm-hmm.
Is it possible, and what would you do to follow the change of the oxidation state of iron at each step of the reaction?
I would look at the partial charge densities of the populated molecular orbitals to see where they are located. So if they are primarily located along the iron center, then I would suggest that there are electrons there and orbitals that reside on the beams of the orbitals of the iron. However, one thing I kind of skipped by because of time, and I can quickly educate, is NO is known as a non-instant ligand. That is to say that it is difficult to discern what the oxidation state is of this iron center. So I may start with an iron 3, but the actual formal oxidation state of that iron can be iron 3 or iron 2 depending on where the pi star anti-bonding electron resides.
Okay, more questions to Zach? If no, let's thank him for detailed answering his presentation. And the next presenter is So he will present another mini research related to chemical reactions on the surface. But in contrast to previous speaker, he will look on the reactions catalyzed by solid surfaces rather than molecular catalysts. Floor is yours.
Thank you, Dr. Disrud, and good afternoon, everyone. So, my study is about catalytic electronic structure dependence on thiophene hydrodesulfurization reaction. So, in petroleum industry, hydrodesulfurization is known as the process of removing sulfur contaminants from natural gas of crude petroleum products to form refined petroleum products. So during this hydrodesulfurization reaction, during this sulfur removing process, the sulfur contaminant hydrocarbon is treated with hydrogen gas in the presence of heterogeneous catalyst at elevated temperatures and pressures to form this refined petroleum products, and hydrogen sulfide is formed as a byproduct. So here you can see a simplified catalytic hydrodesulfurization reaction mechanism in this diagram. So there are several theoretical and experimental studies have been conducted to study this hydrodesulfurization process, and in most of these processes, molybdenum surfaces or molybdenum nanoclusters have been used as the catalyst, and thiophene is used as the probe molecule to study this hydrodesulfurization reaction. So the main objectives of this study is to model the hydrodesulfurization reaction of thiophene on molybdenum surface and study the dynamics of this hydrodesulfurization reaction, and also study the catalytic electronic structure dependence on this hydrodesulfurization reaction. So in this study, as the model system, a thiophene molecule adsorbs a single crystalline body-centered cubic molybdenum surface with 24 molybdenum atoms in excess hydrogen atmosphere is used, and the electronic structure of this model is determined using density functional theory, which is implemented in WASP software. And also molecular dynamic simulations have been used to study the evolution of the position of atoms during heat treatments. So thiophene seems to be dissociatively adsorbing on catalytic surfaces. So catalytic surface, here you can see the variation of carbon-sulfur bond distance during this adsorption process. So as you can see, with time this carbon-sulfur one of these carbon-sulfur bonds are dissociating. This bond is elongating and dissociating. So here you can see the carbon-sulfur bond distance as a function of total energy. As the carbon-sulfur bond distance increases, the total energy of the system decreases. That means the system tends to stabilize by dissociating this carbon-sulfur bond. So this movie further illustrates the dissociation of this carbon-sulfur bond during this the adsorption process. So this further confirms that thiophene is dissociatively adsorbing on these catalytic surfaces. So here also we calculate the binding energy of this thiophene molecule on this neutral molybdenum surfaces, and it is found to be 4.1 electron volts. So if we calculate the binding energy per non-hydrogen atom, it is about 0.83 electron volts, and it suggests that this thiophene molecule is strongly chemisorbed on this molybdenum surface after adsorption. And also our calculated results are in qualitative agreement with experimentally determined data. So then we determined the catalytic electronic structure dependence on this thiophene hydrodesulfurization reaction. So here you can see a thiophene molecule adsorbed neutral molybdenum surface at 0 Kelvin. So at 0 Kelvin only one carbon-sulfur bond is dissociated here, and when the surface temperature is increased to 1000 Kelvin, even though this carbon-sulfur bond is elongated, it is not dissociated, it is not completely dissociated. So this movie illustrates the dynamics of this thiophene molecule adsorbed on neutral molybdenum surface at 1000 Kelvin. So at 1000 Kelvin, this one carbon-sulfur bond is completely not dissociating. That means this sulfur is not removed from this hydrocarbon, and it is not catalytically active to remove this sulfur contaminant from this hydrocarbon fragment. And we also did, so here you can see thiophene molecule adsorbed on oxidized molybdenum surface, moderately oxidized molybdenum surface. So at 0 Kelvin, like in the neutral molybdenum surface, only one carbon-sulfur bond is broken. So when the surface temperature is increased to 1000 Kelvin, there are evidences of dissociating both carbon-sulfur bonds. That means it seems like catalytically active towards hydrodesulfurization reaction, oxidized molybdenum surfaces. So this move illustrates the dynamics of this thiophene molecule adsorbed on oxidized molybdenum surface, and as you can see, after heating at 1000 Kelvin, this carbon-sulfur bonds are instantaneously dissociated at 1000 Kelvin. That means these oxidized molybdenum surfaces can be used as catalyst for hydrodesulfurization reaction. So as conclusions, thiopene hydrodesulfurization is depend on the electronic structure of the surface, and neutral surfaces are catalytically inactive towards hydrodesulfurization, and oxidized surfaces are catalytically active towards hydrodesulfurization reaction. And to remove those adsorbed sulfur and hydrocarbon fragment, we may need to further increase the surface temperature.
Okay, let's thank Tivan. And his presentation is open for discussion and questions. Students attending the course are welcome and encouraged to ask.
Is it 18 points for this?
Yes. Okay, if there are no questions, I have one. So if you follow your own plan, the last word of your presentation, further increase of temperature to induce desorption of your products. What is your expectation? Which of the products will desorb first? Sulfur H2 or hydrocarbon?
Usually sulfur have experimentally sulfur have some high binding energy towards with the molybdenum surfaces. So I am expecting to remove hydrocarbon fragment first at lower temperatures than removing sulfur. So removing sulfur is equally energy required step like hydrodesulfurization process. So during hydrodesulfurization, it is equally known as removing sulfur from the surface, and also the carbon-sulfur bond dissociation. Both are equally determining steps.
Okay. If there are no more questions, let's thank Tivan. Oh, okay.
You
More
didn't
questions.
really mention about your methodology. How you know that the what functional do you use, what basis sets, and how you know that this will be valid for your system? Maybe your data are really affected by taking smaller bases. If you increase the basis, you will see that this happens not at bond breaking is happening not at 700 but much lower temperatures. Do you have any justification of the methodology that you were using?
Experimentally, this reaction is done at around 700 Kelvin, 700 Celsius. So that's why we use 1000 Kelvin. And the methodology, I am not exactly.
But what function did you use?
Would you agree that you used PBE functional?
And actually, it was the same question to Zach, right, and to the previous speaker as well. And I looking on your reports, you explaining methods, but you're not given any details on methodology, what exactly functional you're using, what exactly your basis set, what the size of your unit cells, and so on. Okay.
Approximately, what
Maybe
is
someone
the
tells
size
you.
of
I guess
your
you do know,
what
right?
is the size of
Functional
your
range.
simulation cell? Approximately, how many nanometers or angstrom?
Okay.
7 by 7.
No, nanometers. How big is your unit cell? How big is your simulation cell? It is of the order of the thiopene molecule.
It's in the level of angstrom. It's like
Okay.
about 2 to 3 angstroms.
So the whole cell,
It should. I'm talking about the bond lengths of this
Mhm.
thiopene molecule.
but the whole simulation cell, how big is it?
Maybe about 4 to 5 angstroms.
Hmm?
Maybe about 4 to 5 angstroms. I'm not exactly.
Maybe a little bigger. Okay, let's thank Tivan for a good attempt to answer all questions. And the next presentation continues the subject of catalytic reaction. It is by Brendon Disrud, and I would like to bring to attention that this course was offered to both graded and undergraduate level students to bring the same level of technical skills and cover broader audience. Floor is yours for generous 4 minutes.
All right, I'm Brendon. I was looking at reaction between carbon nanotubes and hydrogen peroxide. A little bit first on all the different types of carbon nanotubes. They're split up into single-walled and multi-walled, but we're going to be using only single-walled and only one specifically, because single-walled are much smaller. And then there's also a specific vector that is applied to the carbon nanotubes, which describes their shape. The single wall versus multi-wall. Single wall is probably your basic one atom thick, and multi-wall is pretty much like a single wall inside of another single wall, and so on. For the vectors that describe them, you can think of them as a graphene sheet, and then vectors along that graphene sheet point to another carbon that you would roll up into a tube and connect them there. So the three types that we could get when we do this are zigzag, where one of the pairs of vectors is a 0. So I've tried to highlight them in these pictures here so you can kind of get your mind around them. And we're going to be using zigzag, but there's also chiral vectors, where it's 2 unique numbers, and armchair, where both of the pair of vectors are the same. So we use the 4, 0.